So, when we talk about a lot of electronics, there's a couple major heat problems, and that is one, they're very sensitive to water damage, so that's a huge problem. Secondly, they overheat a lot, and that's another huge problem. Thirdly, there could be arc discharges, which means that electronic component is damaged and electricity goes from one place to another place, which cause more damage. Then there's corrosion and dust getting into the whole thing. Another problem with everything is that it could even catch on fire. So I have a proposed solution for all this, and that is replacing the air inside of these electronics with a certain type of liquid nanoparticle mixture. This will be a liquid that has a lot of certain types of nanoparticles in it. And then with these nanoparticles, what this will do is it will prevent water and other damage by displacing the water and acting as a hydrophobic thing. But beyond that, it would also stop dust and stuff from entering. It will act as an antioxidant or barrier to oxygen, preventing corrosion from that method. So this acts as a barrier and prevents corrosion, and act as an antioxidant from a variety of things. It will also act as an insulator in many ways, preventing discharges, and a little bit of a fire suppressant. So how would we do this? Well, and what's my evidence of supporting everything I'm saying? Well, air is only 0.0262 watts per meter Kelvin conductivity. You don't have to understand that unit, but watts is a unit of energy. Meters is a unit of distance, and Kelvin is a unit of temperature. Kelvin and Celsius, 1 degree raised in Kelvin is the same as 1 degree Celsius raised. Is just that they start at different points. Where 0 degrees Kelvin is absolute freezing and 0 degrees Celsius is freezing water. So you could even do watts per meter Celsius and it would be the same. But the units are not the most important here. It just tells you how much energy is transmitted. It's just a unit based on the two principal factors, that the amount of heat energy is depending on the difference of temperature. The bigger the difference of temperature, the more energy will transmit faster, and the distance, the bigger distance that travel, the less energy gets through to that distance. But air is a pretty good insulator, 0.0262. And it's more that the number is very small. Now let's go down to oil. So there's going to be a bunch of different oils. And this to make sure that the oil, and I'm getting all my numbers from Engineering Toolbox, olive oil is 0.17, already about 10 times bigger. Silicone oil is about 5 times bigger. There's also silicone oil. Then let's look at some other ones. Ensign oil is about a little over, about 7 times bigger. About. And then there's a bunch of other oils that are even better ones and less good. And all these oils do protect against oxidative damage, but they also displace water and are hydrophobic. And they're also cheap. You can make them better with a process where we add halogens to them. Halogens include fluorine, chlorine, bromine. The problem with halogens is that, yes, it'll make it better conducting heat and more electrically insulating. And it'll also make it more dense, which in some ways can be advantageous. However, halogens are usually slightly toxic and prevent the whole thing from breaking down as much. And they're harder, the more toxic in nature. You could It also does some haldens. The process to make the haldenate stuff is not the most green, and spraying them on stuff is not the most green, but it's easier to spray with them. Usually fluorine is the worst, then chlorine, but there's also bromine, which is below them, and I think bromine might be a little bit better because it's less reactive, and it's also more common and easier to synthesize in green roots. But I haven't heard of brominated oils that much. But maybe a little bit is not that bad of a deal if it comes with a lot of advantages. So first of all, we have these oils that are very, very good also for themselves because they make stuff very slippery, so easy to pump in. But we fill up most of these oils with something that's a lot better, and that is copper. So this chart is a little different. And I'm going to go through it because it's a little different. Copper comes in many different forms, and this is the temperature in Celsius. Room temperature 20 to 25 is like a reasonable estimate for room temperature. And there's many different forms of copper, but high quality copper has 390 compared to our 390 watts per meter Kelvin. 390, that is almost 4,000. That is almost a straight up 20,000 times more conductive than air. So if you mix in a lot of copper nanoparticles into this, and you can get over 60% of this being copper nanoparticles, you can get a ton of heat conduction, a ton more than air could ever do, and make it a ton more even. And you would have to coat these copper nanoparticles with a thin layer of a polymer of some sort, which is a thing that has repeated linked chains. And you can do that with graphitization, where you coat it with carbon, which is even more conductive, but it won't be a very big thing because there won't be very big because that'll be such a thin layer. The reason why not a thicker layer is because carbon right now is very expensive. If we make cheap carbon nano onions, that might be better. Then you would have to take those carbon particles, and to make them not conductive, you have to oxidize them slightly at the surface, or fluorinate them or sulfonate them. So that would be very, very highly conductive and make this whole thing carry electricity. And if over 60% of this is highly conductive thing, you've just made the whole thing hundreds of times more conductive than air and getting heat. Now this does make it less of an insulator, but the oil and stuff in between will make it more of a electrical insulator and repel and it will also act as more of an antioxidant. Plus you have other things going for this thing with the copper itself is also an antioxidant when broken down, and copper is a little more safe. You could also, to make this whole thing oil, other modifications to oils, you could nitrate it, which would make it more thermally conductive, but you have to figure out how to nitrate it or sulfonate it. And that actually might be more environmentally friendly because nitrated organic compounds exist all the time in nature, and actually some of them have heart benefits. So even a little bit of nitrate might do it. But that'll be fancy because nitrate has antioxidant properties, but some of it has oxidant properties. So I'm wondering back and forth in my head how to do that, whether that would be good. And this oil, some of the best oils are not come from plants. Actually, so it wouldn't be that bad naturally compared to a lot of the mining oils. Now, what if you want to repair this whole thing? How would you do that? Well, this would be something that you could easily just suck up and remove it that way. Or just rinse it off with alcohol, which doesn't hurt discs as much. Then if you suck it up or rinse it off with alcohol, you can recycle it. Well, thank you very much for listening. Please like and subscribe. It really helps the channel out. I'm trying to reach 1,000 subscribers in a year and 4,000 watts hours, which is really hard. With your help, I think you can do it. Thank you very much again.